Hello friends, so welcome to the 22nd lecture of this course. So in the last lecture we have learned few results about normal matrices. In this lecture we will discuss another important class of matrices, those are called positive definite matrices. So as we know that if we are having a symmetric matrix, then all the eigenvalues are real. That is true, and we have seen the proof of this in the previous unit. However, what is additional, we will learn in this lecture that the eigenvalues are not only real but positive also, or just non-negative. So a square matrix A is called positive definite if it is symmetric and for a non-zero vector x, x transpose into A into x, which is a scalar and it should be positive. So whatever non-zero vector you take x, x transpose A into x should come out to be positive. If this is true, then we will say the square matrix A is a positive definite matrix. In short, I am saying it PD, P for positive and D for definite. The same definition in other words can be written like this: x transpose into Ax greater than equals to 0 for all x, and this particular expression x transpose A into x will be 0 only if x equals to 0. So this is the definition of positive definite matrix. A square matrix A is positive semi-definite or PSD in short if it is symmetric and x transpose Ax is greater than equals to 0 for all non-zero x. So the only difference is positive definite and positive semi-definite is here it will be strictly greater than 0 for non-zero x, here it may be 0 also. The example or I will say the trivial example of a positive definite matrix is identity matrix. So that a symmetric matrix A whose eigenvalues are positive or non-negative is called positive definite. So here what we need to prove, we are having a matrix A, let us say n by n matrix, and we have to prove that if all the eigenvalues of A are positive, then it is a positive definite matrix, and if all the eigenvalues of A are non-negative, then it is a positive semi-definite matrix. So let us take an eigenvalue lambda, let lambda be an eigenvalue of A and x be the corresponding eigenvector. So here lambda is eigenvalue and corresponding eigenvector is x. It means A into x equals to lambda into x. Now multiply both sides by x transpose. So x transpose A into x will become lambda x transpose into x, or I can write it lambda equals to x transpose A x upon x transpose x. Now if lambda is positive, this means x transpose A x upon x transpose x is positive. Since denominator will be always positive, so it means x transpose A x is positive for all x belongs to, this means A is a positive definite matrix. Similarly, if lambda is greater than equals to 0, this means x transpose Ax is greater than equals to 0 for all x belongs to Rn. And please note here x is eigenvector, so they will be non-zero vectors. So, in this way we can prove that if all the eigenvalues of a matrix are positive, then the matrix is positive definite. If all the eigenvalues of a matrix are non-negative, then the matrix is positive semi-definite. Alternate definition for positive definiteness can be given like this. A real symmetric matrix A is positive semi-definite, or I will say positive semi-definite if and only if A can be factored as A equals to B transpose into B. Further, A is positive definite if B is non-singular. So, the proof can be seen like this. So, A is positive definite or positive semi-definite if and only if A can be written as B transpose into B. So, since A is a symmetric matrix, we can always find a matrix P such that A equals to P into D into P transpose, means since A is symmetric, so it will be always diagonalizable. Now, what I need to prove that A can be written as the factor of two matrices, that is B transpose into B. Now, this can be written as P, since A is positive semi-definite, so eigenvalues of A will be non-negative and hence all the diagonal entries of D will be non-negative. So, I can write this D as D half into D half, where the entries are square root of the original D into P transpose. So, if I choose B as D half into P transpose, then from here I can write A equals to B transpose into B. If all the eigenvalues are, means if B is non-singular, then all the diagonal entries of D will be strictly positive and hence A is positive definite in this case. So, in this way we can prove this result. There are few more tests for checking whether a given matrix is positive definite or not, and one of the test is based on the leading principal minors. So, a real symmetric matrix A is positive definite if the leading principal minors of A are positive, or all principal minors of A are positive. Here positive means having the positive determinants. Let us check all these results for a given matrix. So, check the following matrix for positive definiteness. The matrix is 2 minus 1 0 minus 1 2 minus 1 0 minus 1 2. So, the matrix A is given, which is given as 2 minus 1 0 minus 1 2 minus 1 0 minus 1 2. So, we have to check whether this matrix is positive definite or not. So, there are different tests. So, let us take the first definition. Let X belongs to R3 be a non-zero vector So, means x equals to x1, x2, x3 transpose. So, now x transpose A x will become x1, x2, x3 into 2 minus 1 0 minus 1 2 minus 1 0 minus 1 2 into x1, x2, x3. This comes out to be 2 x1 square minus 2 x1 x2 plus 2 x2 square minus 2 x2 x3 plus 2 x3 square. This I can write like this: x1, so minus x1 x2, so minus half x2 whole square. So, if I express it, it will become x1 square 2 x1 square. So, x1 square is left out here, and then 3 by 2 x2 minus 2 by 3 x3 whole square plus 4 by 3 x3 whole square. So, the above thing can be written in this way, and you know that the final expression is the sum of square terms. So, this will be always positive for non-zero x. Hence, A is positive definite, because xTax is always positive for non-zero vector x. This is one of the way of checking the positive definiteness. Another way is by calculating the eigenvalues of the matrix A. So, if we check the eigenvalues of this matrix A, which is given like this, the eigenvalues comes out to be lambda equals to 2 plus minus root 2. So, eigenvalues are lambda equals to 2, lambda equals to 2 plus root 2, and lambda equals to 2 minus root 2. If we check, it is positive, this is also positive, and this is also positive. So, all the eigenvalues of A are positive. This implies that A is positive definite. Another test is by checking the minors, principal minors. So, matrix is 2 minus 1 0 minus 1 2 minus 1 and then 0 minus 1 2. So, let us take first this minors. So, A1 which is 2 which is greater than 0. Now, check the 2 by 2 minor. So, it will be this one. So, this is the determinant of 2 minus 1 minus 1 2. This comes out to be 4 minus 1 which is 3 greater than 0. Now, check the determinant of A, that is that 3 by 3 minor, minus 1 2 minus 1 0 minus 1 2. So, if I check this determinant, this will be 2 4 minus 1 minus minus plus 1 minus 2 plus 0. This comes out to be 6 minus 2 equals to 4, which is also 0. So, all the principal minors are positive, and hence the matrix A is positive definite. So, in this way I have told you 3 different methods to check whether a given matrix is positive definite or not. What are those? The first one, just take a non-zero vector x and find out x transpose x. If you can write that thing as a sum of perfect squares, then the given matrix is positive definite. Number 2, find out the eigenvalues. If all the eigenvalues are positive, then the given matrix is positive definite. If all the eigenvalues are non-negative, then the matrix is positive semi-definite, means some are positive and some are 0. The third is minor test. If all the principal minors are positive, then the matrix is positive definite. In the same manner, we can define the negative definite matrix. A square matrix A is negative definite, in short I will say it ND, if it is symmetric and x transpose Ax is less than 0 for all x, means for all non-zero x. The equivalent conditions are A has only non-negative eigenvalues, the determinants of A's principal sub-matrices are negative, or A has negative pivots. These are the equivalent conditions. Like the test we have seen for the previous example, just the same test but in negative sense to prove a given matrix as negative definite. In the same way, we can define the negative semi-definite, and that symmetric matrix is negative semi-definite if x transpose into x is less than equals to 0 for all x those are not 0, then the matrix is called negative semi-definite. Means if a matrix are having the eigenvalue 0 and negative, then the matrix is negative semi-definite. Now, another important definition related to definite positive and negative definiteness is quadratic form. So, for a vector x which is a real vectors in open having n components, and a matrix A which is a real matrix of size n by n, the scalar function defined by f(x) which is x transpose Ax, and in summation form, if the entries of A is denoted by Aij, then it can be written as I equals to 1 to n, j equals to 1 to n, Aij xi xj is called a quadratic form. Further, a quadratic form is said to be positive definite, positive semi-definite whenever the matrix A is positive definite or positive semi-definite. This is the real quadratic form. In the similar manner, we can define the complex quadratic form. So, let x be a complex vector having n components, and A is n by n matrix having complex entries, and A is Hermitian. Then the expression f(x) x star Ax, which is comes out to be Aij xi xj conjugate, is called a complex quadratic form. For example, if a matrix is given to you and someone asks find out the quadratic form of this matrix. So, let A is given to you, which is 3 minus 1 2 minus 1 2 0 and then 2 0 1. Find the quadratic form of let x1 x2 x3 be a vector in R3, then the quadratic form of A is defined as x transpose Ax, which is x1, x2, x3 multiplied with matrix 3 minus 1 2 minus 1 2 0 2 0 1 into x. X is x1, x2, x3. So, this comes out to be 3 x1 square plus 2 x2 square plus x3 square, because these square terms will be just multiplied with the diagonal elements. The diagonal element of first row will be multiple of coefficient of x1 square, the diagonal entries of second row will be the coefficient of x2 square, the diagonal entries of third row will be the coefficient of x3 square minus. So, minus x1 x2 will come from here and x2 x1 will come from here. So, minus 2 x1 x2. Similarly, 2 x1 x3 will come from here, 2 x3 x1 will come here. So, it will become x1 x3, 2 plus 2. So, it will be 4. So, 4. The coefficient of x2 x3 will be 0 as well as for the coefficient of x3 x2. So, this is the required quadratic form of the given matrix. If someone asks to check whether this quadratic form is positive definite or positive semi definite or negative definite or negative semi definite, what you have to check? You just check this matrix A. If A is positive definite, the quadratic form is positive definite. If A is negative definite, the quadratic form is negative definite, and similarly for positive semi definite and negative semi definite. Well, in this lecture we have learned the definition of positive definite matrices, positive semi definite matrices, negative definite matrices and negative semi definite matrices. Later on we have learned few tests how to check whether a given matrix is positive definite or not. Apart from that, we have learned quadratic form relating to a matrix. In the next lecture, we will learn some other important properties of quadratic form. We will learn the diagonalization of the quadratic form. We will learn some applications of the quadratic form, in particular to draw a given quadratic curve with the help of quadratic form. With this, I will end this lecture. Thank you very much.